Hey everybody, it's Jagannath from digitronixnepali, and today I'm gonna share with you how to how to get the highest throughput through any function you want. Okay, it's not just for cryptography or mining application, just for any you can use any function and get the highest throughput with the methodology that I'm gonna describe now. Okay, let's get it started. Okay, so this is some. Let's get started with some basic thing. Okay, let's say you have got a function. We don't care what function is it, but let's say you have got a function. So this is the basic way of using that using that function iteratively and getting the output. So we have got one input, and that input is passed through this register to this function for the first time, and after it gets input, then that and the output of that function is again fed into that function again in every clock cycle. And depending upon the algorithm or the output desired, this loop may be repeated like 10 times, maybe for some application maybe 20 times, 30 times. It depends upon the application. Okay, let's take for example of Keccak. Okay, in Keccak, this loop has to be repeated, iterated 24 times. So it will depend upon the algorithm. So what are the characteristics of this design? The first characteristics, it has the latency same as the number of loop cycles. So if it has got 24 cycles, then we have if it is repeated 24 times, then it has got latency of 24 clock cycles. So in case of Keccak, it's 24 cycles. And the main advantage of this design is it has got the minimum area, and throughput is also minimum because you have to wait 24 cycles until you get to input new value. So until the first output until we get the first output, we won't be able to input new input in this module. So that's its main disadvantage, and this is not desirable, of course, for a higher hash rate generation. So let's look at another module, another design. So this is another design, and in this case also we just give input through this demux, and we pass through the function, but this function is unrolled number of times, like maybe 4 times or 8 times, or any number of times you want. You won't be able to this stack this like this forever, but for up to like depending upon the function, you may be able to put this up to 8 times or 12 times, something like that. And the advantage of this design is that your latency will be a lot less. Like if you just give two functions in the Keccak, then you will get output in 24. Instead of 24, you get output in 12 cycles, right? So you are likely to get higher throughput in some scenario if a function has a less critical path. But uh, but what happens if you just stack this function over and over again? You will have the very high critical path delay, and you won't be able to clock your FPGA faster. So this is not desirable. So this latency will be less, but it will consume higher area, and it will also it won't support the higher frequency also. So its maximal allowable frequency will be less. So this is not desirable in in maximum throughput generation. So this is I think the worst design of all. So now today I'm gonna this is the design that today I'm gonna discuss in detail. This is the best favorite design for mining application in most of the algorithm. So we've got input over here, and we got register, and we have function, and we have got register again, function again, register again, function again, and we go on up until we repeat this register function block the number of that many number of times. Like for Keccak, we repeat this register and function 24 times. So there is new function for every iteration, every iteration, let's say. So the main advantage of this design is you can give input and it will go over here in first clock cycle. In second clock cycle, it will go over here, and you don't have to wait until we get output. We can give input every clock cycle, right? So you get the uh, maximum throughput with this design, and it has less critical path also because we have used registers in every pipeline stage. So it will have less critical path, and that will make we will be able to clock the frequency or even overclock the FPGA. So to up to maybe 400 500 megahertz. So this is the most desirable design for mining application or some high throughput application. All right. So this is the combination of that pipelining and basic iteration. I won't go into much detail here, but in this case, we will be able to give input in every 4 clock cycle. So now I'm gonna show you how to write Keccak from scratch, almost from scratch, and get the highest throughput. Like we'll be able to get around 12,000 million as per second. Let's get started. Okay, there is I have already opened the project, and this is Keccak, and Krishna sir has already mentioned how to use this component and instantiate it. So I won't go into much detail here. Yeah, and you don't need to know what goes inside this component. That's not important. It's out of the scope of this webinar. Today I'm going to show you how to use this component, like instantiate it, how to use this component to get the maximum throughput. Okay, let's get started. First of all, you need all the signals to go for, like let's look at that. Okay, you need a register over here. So let's declare all these wires over here, and we have lot of wire in every register for input and output of the register. So let's declare some like we have got 24 registers, so we need for input and output of the register we need 48 such signals. So let's get started. Signal, let's say R in 0 and R out 0, and these are the signal for register in and out. It's a standard logic vector. In case of Keccak, this value is 1600. It has got 1600 bits. So this is a signal, and we need this up to R in 24 and R out 24. So I'll just use shortcut here, just Control D up to like 24 times. I think I got that. And just use over here, just use Alt and Shift and down arrow key. Alt, Shift and down arrow key, and you will be able to select like this, and just press Alt C, and let's start from 0 and increase by 1, and we're good to go. Yeah, oh, I got 35 of those. I don't need them. From 23 I can just delete it. Okay, and same with R out, and yeah. Okay, now I can instantiate sorry, I just used this begin here. Begin should be later. So let's instantiate that component is let's UUT. You can use UUT, and that component name is round F. So this is one round of Keccak, and you don't need to know the details of it right now. And as you can see, the ports are clock and R in for R in, and R out and round constant. I'll declare a round constant later, but these are basic. Basic way of instantiating the component. So we need, as you have already mentioned, we need 24 of the register. We need 24 functions too. So let's make it 24. Same process as above. Let's Control D. Maybe I've got that. And Alt Shift. I just need to write. I forgot the semicolon over here. Just insert semicolon. And I need R in 23 and R out. Same with R out. Okay. And I need round constant also. Now I need to declare the round constant. And for round constant, you can just look at the Keccak official website, keccak.team, and you can just, okay, maybe you can Keccak team spec summary. Okay, you can go there. The link will be in description, and you can see the round constant over here. This is round constant, and here's a secret to decrease the area. Like I'll just tell you some secret to optimize. You don't need to know. This will be different for different algorithms, but for Keccak, you can see like these are round constants. If you look at closely here, they have got similar pattern. Like there is a lots of zeros over here on these bits, and all these are redundant. We don't need all these zeros values. If it is deterministic, then we can optimize it. If it would be non-deterministic, like if it would be random numbers, it would be harder to optimize. So this is a bit easier to optimize because you can see some redundancy component here, and it's deterministic. So the you don't this would be, if we use normally, then it would take 64 bits, but it's already now, yeah, but uh, as all these bits are redundant, we don't need 64 bits, and I will just use 7 bits instead. So let's declare the constant value for round constant. That would be RC, and that would be standard logic vector 7 bits, so 6 down to 0, and I'll need 24 of them. So just Control D and more of them, and that would be from 0 to 23. Right, and its value would be, I have already stored this value, C, and that would be, I forgot this. So I need to store, okay, and I need to paste that round constant over here. Okay, we've got some little problem while pasting it, so I'll just use it from, I have already written that constant value. I'll just use this from here. So yeah, okay, that's it. Now I need some, okay, that's we I'll just skip this also. All right, now we're good to go. So what I've done is I have just instantiated all these rounds, and I have given the R in 0, R in and R out for all of them, right? This is single round, and this is another round. We have 24 of this all rounds. So from the presentation we can see what goes. Like from the output of round 0, this is round 0 suppose, and from the output of round 0 it goes to through register, it goes to input of round 1, right? So let's make that. So and that happens in every rising edge of clock, that would be register. So let's make process, and that would be sensitive to clock, and begin. And I just need if rising edge of clock, then I just need R in is R in. R in should be another, the R in of the second round should be R out of first round. So let's make this like this, and same as again. Control D, something more, and I'll just be the R in of first module should be, second module should be R out of first module. So 0. So here it is. The output of R out goes to R in rising edge of clock, and that's what we want. And we don't need all of this. And this end if and process, and we're good to go. So the Keccak is almost completed, but we need some little bit extra things, like we need to, the input here is 512 bit, but the state of Keccak works in 1600 bits, so we need to pair it before we pass it to these states. So I have got padder. This is constant. You can just paste it here. This is padder, and like we're just good to go. And one thing more, this Keccak has the Indianness of Keccak is different from the normally we use. We need to swap the bytes before we use for Keccak state. So for that, changing the swiping the bytes and changing the Indianness, we need another component called index relocation. We don't need detail. It's a simple function actually, but we won't go there. It's just swapping the bytes. So let's put that function also. Let's declare some signal first, and we are finished. Signal, like it should be padded, right? Let's call it is 1599 down to 0, right? This is my padded signal, and for that padded we need some like padded should be a D in, and we just need to pad this padder, so this is padder bits, and I just padded it to D in and to get this signal padded. That's it. Now I need to swap those bits, and let's call that name swap, and index relocation in is that, and I need to pass this padded value, and this value should be given to the input of this round, that is R in 0. So if we give first input from padded value, and it goes on and this round will take on from there. Now I need to take the output. Output would be the first 512 bit of this round 23. So it should be this 512 bits of this round of this output. So that would be round 23. So uh, let's keep that. And finally, we need to swap the bytes again at the final time also. So let's call it swap 2, and there should be index relocation in, and oh, I forgot the port map. All right, in relocation in and port map, and that should be around out 23. This is our output, and we need to change the Indianness, and let's call it final, right? And I need to declare that final signal also, padded and final, right? That's it. Like, we're good to go now, and let's create a test bench over here. Okay, this is test bench, and for creating test bench, I'll just use the shortcut. So this is our code, and for test bench, we can just go to this dollars site. We'll just link this in description. Just paste it, and it will get that component initialization. Just put it like this, and I just need to paste it in test bench. Sorry. Okay, here it is, and I need to give the instance the d in some values. Let's give some input. Like, I have some random 500-bit input data. I'll just keep that, and let's wait for a 20 like, okay, 1 clock cycle. We can give new input every clock cycle, so we'll get the maximum throughput possible. Okay, so this is waiting to 10 clock. Let's give another input. Uh, let's just change little bit. Instead of 0, let's keep it 1, right? And just wait for 10 nanosecond, and just repeat this few more times. And instead of 1, let's keep 2. Instead of 1, let's keep 3, 4, and let's wait for 1000 nanoseconds more. So we're good to go. I'm expecting some error. Maybe we may get some error, but let's test. Okay. R24, I've got one more modules. We can just test it here. R24 is not declared. I just forgot 24. So yeah, I must have some R24. I'll just declare. All right. 136. Sorry, I just made this extra. So yeah. And yeah. Okay, let's keep this over here. I need to change this to cell. Okay, sorry. Keccak 4. I'll just keep Keccak 4 its name, and its name is Keccak 4, I guess. And I'll just use this. I'll just disable it. Okay, we've got some output. Okay, let's test this. Okay, for example, we have given input here over here, and we are giving input in every clock cycle. We have not given much input, but we can test for a few times. Like this is our input, and we're getting output over here, and we're getting output. This is the main thing. Like we are getting output every clock cycle. You see, so this is getting the maximum throughput possible. Okay, and let's check input and output test. Let's check the input. Like this is our input, and the way to test is there's a website. I will link this website also in description. I'll just paste it over here and just select the Keccak and calculate. We are getting 7C08, something like that, and we must see same output over here. Like if we change the input to like if we give this input, second input, and we paste it that over here, we're expecting the output to be 52 E924, E924, something like that, and we're getting that output. So we're getting
Okay,
new
great.
output
So this is so great.
every
So
clock cycle.
Jagannath have started
Uh,
from the scratch and he's also saw the simulation.
yeah.
So that's great. So guys, you already know the basics of Keccak, and actually we have the sessions on AES, and we would like to have that AES session in next one. So our 60-minute time has been up. So guys, thanks for your time and the participation, and we are thankful to Jagannath. He is showing from very much scratch of Keccak to the simulation, and he verifies the results. And what is the hash rate currently we are achieving with Keccak,
Okay.
Jagannath?
Okay, this single instance, okay, will result in 600 million as per second. But the plus point of it is this is getting utilizing around 4% of high-end FPGA board of like
Wow,
VCU1525.
that's really nice. Yeah.
Yeah,
So
yeah,
we
it
are
will only.
consuming too less resources.
Yes, to get, and we're getting 600 million hash per second if we calculate. Like we are getting every output at every clock cycle. That means
Mm.
we can get the like we are getting the equal hash rate as the clock rate of VCU or some iron boards. And as iron boards can support up to 600, 700 megahertz. So we are getting
So
like
that's really
that's
great.
yes. And
So
so
guys, thanks for your
and
time.
one point is like we are using only 4% of the resources with such extreme hash rate. So we can multiply
Mhm.
use this instance multiple of times. Like for if we
Yeah,
are using 4%, like we can instantiate it, all this block 25 times to get the
yeah,
utilize
great.
100%.
Mm.
That would
Mm.
multiply the hash rate 25 times also. So we can get
So
12
that would be
gigahash
equal
or
like how
13
much?
gigahash per second. Azure? Yes,
Okay.
that
So
will
what is the
result in
total
12
hash
to 13 gigahash per second. 600
rate?
million hash
Okay.
per second times 25 equals like maybe 15 gigahash per second, something like that. So we
Okay,
can get that.
that's really great. That's really great.
Yeah,
Okay. So it's really nice to have this type of real-time simulation also. So
yeah.
Jagannath, thanks for your plan
Okay,
and
thank
thanks
you.
for your everything you are showing up.
Yeah, yeah, yeah,
And
yeah,
we would like to close up this session. So thank you
yeah.
for everyone. for participation. And we'll also have this recording in the corresponding email, so you guys can also watch the recording, complete recording. And if you have any queries, you can just write us to info@logictronics.com, or the email which we have provided on email. So guys, thanks for your time. We would like to stop the session
Thank
and
you.
meet you in next similar session.